Our discussion of partial fraction decomposition was really aimed at trying to get us to solve the differential equation here on the right, which is the differential equation that goes with a logistic growth model. So a logistic growth model is one that will model populations most often. So for instance, biologists would probably be very interested in this type of growth because generally a population will start off growing, but then it'll approach a carrying capacity due to limited resources, predators, things like that. So just to give you the correct analogy here, we started with exponential growth models, and we noted that the rate of change of the population over time is directly proportional to the population at that moment. And the result is a picture that looks like this. You can see the exponential growth graph, which is probably familiar to you. So if you want to model a population that starts growing exponentially, as we see here on the right, you can kind of see the concavity represents an exponential function, at least at the beginning. However, it changes. It changes to become concave down. If you want that to happen, what you need is, so notice the differential equation starts off, ignore what's in the blue box, it starts off like an exponential. But if you want it to start flattening out, what you need to have happen is you need the derivative to start approaching zero. And so if we call this the t-axis, and this is the population axis over time, then what's happening here, this is m, that's the carrying capacity. That's the maximum, sort of the maximum level that a population could ever get to. What you need is as the population approaches the carrying capacity, we would want the derivative to approach zero. So you can see that as m and p, or as p approaches m, that term there is going to go to zero, which is what's responsible for the flattening out of this curve. So this differential equation, mainly you're going to be responsible, at least my students, you're mainly going to be responsible for analyzing the differential equation itself, not necessarily solving it. I will solve it in one of these videos, but that's not actually the point of it. It's to analyze the differential equation itself. So we'll do that on the next slide here. So this is more of a typical type of problem that you would come across, or one would come across in the AP exam. You're given the differential equation, and the first thing you'll need to do is just recognize that this is modeling a logistic growth. This is the differential equation that goes with logistic growth. It says the growth rate of a population, P of a deer, in a wildlife preserve is modeled by the differential equation dp dt equals this. So you'll want to kind of form fit here and notice that this does have the form Kp, so our K is 0.0008, M minus P, where our M is 500. And as long as you know what those values mean, you can answer these questions pretty easily. So it says, what is the carrying capacity for the deer? That's easy. It's just 500. Right? It's in the 500 is in the spot where our carrying capacity should be. The next question says, what's the population when the population is growing the fastest? So let's focus our attention on when the population is growing the fastest. Well, the population would be growing the fastest when the derivative is a maximum. So let's just note that. That's going to occur when dp dt has a max. Right? Notice it doesn't say when is the population a maximum, when is the population a maximum. It says when is the population growing the fastest. So let's find the max of the derivative. That's when it's going to be growing the fastest. Find the max of dp dt. So to do that, let's take the derivative of dp dt. Now the first thing I think I'm going to do is I'm going to distribute this 0.0008 p to both of these terms. 0.0008 times 500 is 0.4, so you get 0.4 p minus 0.08 p squared. that makes it easier to take its derivative, because its derivative would therefore be, I'll use this notation, its derivative is just 0.4 minus 0.0016 p. Now first of all, notice that this is a parabola. It's a parabola that opens down, so we can kind of ignore the principles of finding a max. I'm pretty sure that we're going to find the max if we just set this equal to 0 and solve. So 0.4 minus 0.00016 equals 0. Whoops, where's my p? Oh yeah, there it is. Solving that for p, you get p equals 250. And I want you to notice this is half the carrying capacity. And that will always happen. So here's our logistic growth curve. You know, the population, we don't know the initial population, but a logistic growth curve will start like this and flatten out like that, where that's our carrying capacity. So in our case, the M is 500, and right at 250, right here, that'll always be when the population is growing the fastest, half of the carrying capacity. And you can see that's an inflection point. And you can prove that if you just replace the 500 with an M and solve this, you'll just get that the max is going to happen at M over 2. All right, so that is an invariant. That'll always be the case. The last question says, what is the rate of change of the population when it's growing fastest? Well, that just means we want to evaluate dp dt, and we want to evaluate it at when p is 250. So that ends up being 0.0008 times 250. I'm running out of room here. That clearly didn't help. I'm going to erase this. I'm going to come down here. So it's going to be 0.0008 times 250. 500 minus 250. And if you put that in your calculator, you end up getting it equals 50. And the units on that would be, since this is dp dt, right, it's going to be deer per year. So 50 deer per year. So that's the slope of the curve right at that inflection point. And that is the rate of change of the population when it is growing the fastest. All right, so here's this example is something that you'd want to understand, because mainly on an AP exam you could be given a question like this, and you'd just be expected to be able to analyze it from the differential equation. Notice we didn't even solve this differential equation. We just answered questions based off of the differential equation itself.